Hey guys, this is Mrs. Harbin, and this is part 2 of section 5.5. We are looking at trig ratios and trig identities and proving things, or proving equality, if you will, with trig identities, proving our trig identities. In the first part, we talked about what an identity is, that it's an equation that's true for all values in the domain of the variable, so all the x values, it's true. And we talked about two different trig identities. The first is the reciprocal identity, which says that cosecant is the reciprocal of sine, secant is the reciprocal of cosecant, and cotangent is the reciprocal of tangent. We reviewed the trig ratios, and then we looked a little bit at the Pythagorean identities and where those came from this idea that x squared plus a squared plus b squared equals c squared, or in terms of the Cartesian plane and the unit circle, we have x squared plus y squared equals our radius squared. X squared plus y squared equals r squared. And we looked at the three trig identities that you need to know. Cosine squared plus sine squared equals 1, and you can rewrite that in terms of cosine or sine. Tangent squared plus 1 equals secant squared, and 1 plus cotangent squared equals cosecant squared. And again, you can rewrite all of those in terms of their trig identities, and if you want to know the proofs for those, you can look on page 247 or 248 of your books. And then we talked about the things that we need to keep in mind before we start proving identities. And I'm not going to go through all of those again. You can look at the end of part 1 to see those. But remember that every step in proving an identity must have a reason. You have to have a definition or an algebraic reason to prove an identity. And the reasons involving trig definitions, these reasons involve either trig definitions or algebraic properties that are used to simplify. So when we are proving these trig identities, we're going to be using primarily definitions and algebraic properties, identities that already exist, things that are already proven to be true. So let's start with an easy one. We have sine theta over cosine theta equals tangent theta, and we want to prove that to be true. Now remember, our first step said to choose one side of the statement that we are to prove. We'll usually want to select the more complicated side. So our more complicated side, let me turn on my ink pen here, is this side. So this is the side that we are going to prove. And we are going to go step by step until we can make this side look like this side. We want to prove or take the steps that we need to take to show that this is equal to this. So the first thing that we're going to do, using a basic definition of algebra, we are going to say that sine theta over cosine theta is equal to sine theta over cosine theta. This is our reflexive property of equality. If you've forgotten these things, that's A equals A, B equals B, C equals C. We know that something is equal to itself. So the first thing we do is write this more complicated side, and we're going to say that it's equal to itself using the reflexive property. We're then going to apply a basic definition to our side here. And we know that sine theta is the same thing as y over r, and cosine is just x over r. If we go back to that unit circle here, that triangle, right triangle that we had, okay, this is x, this was our y value, and then this is our radius, which is going to be equal to 1. And the sine of this angle here is, if you remember, sine is opposite over hypotenuse, so that's y over r, and cosine is x over r. So we just replaced those here. We substituted those in based on our definitions of sine and cosine. So that's a definition of our trig ratio. We're then going to simplify this. So y over r divided by x over r is the same thing as y over r times r over x. And when we multiply that, our r's cancel and we get y over x. So sine theta over cosine theta is the same thing as y over x. And based on our definitions that we came up with before, remember we said that tangent was opposite over adjacent. Well, the tangent of the theta is opposite over adjacent. So based on our definition of trig ratios here, y over x is the same thing as tangent theta. And then we're going to write our final step here of sine theta over cosine theta equals tangent theta. And that is based on our transitive property of equality. If it's equal to y over x, and y over x is equal to tangent theta, then sine theta cosine theta equals tangent theta. Remember, that's if that A equals B and B equals C, then A is also equal to C. That's that transitive property of equality that we applied there. So there's our proof. We went step by step to show how we can travel from sine theta over cosine theta and simplify that to tangent theta. So we have proven that identity that tangent is just sine over cosine. You should already be familiar with that because of our unit circle. If we take our sine values on the unit circle and divide them by the cosine values, that's how we arrived at those tangent values all around the unit circle. Let's try one that's a little bit harder. We want to prove that sine theta secant theta is equal to tangent theta. Again, we want to have a step for every reason. We want to choose one side of the statement that we're going to prove, and we want to prove the more complicated side. So we are going to start with this side, and we are going to take steps to prove and kind of simplify down to tangent theta, and that will prove that these two things are equal. So the first thing, again, we want to do is rewrite this as a reflexive property. So we're going to say sine theta secant theta is equal to sine theta secant theta. That's our reflexive property. We then want to rewrite this secant theta. If you remember, one of the steps I said on the previous video is that sometimes when we find an identity difficult to prove, if we change each member to its basic ratio definition and simplify, it makes it easier. So this one is already in sine, cosine, tangent, one of the three basic ones. So we're going to rewrite the secant as one of the three basic trig ratios. So we're going to write secant as 1 over cosine theta, and we know that to be true because of the reciprocal identity, that secant was the reciprocal of cosine. Okay, we're going to just keep on simplifying this right-hand side. We're going to go step by step, and remember, we're trying to get that right-hand side to tangent theta. We're then going to multiply this. This is just an algebraic principle. Sine theta times 1 over cosine theta is just sine theta over cosine theta. And we just proved sine theta over cosine theta to be true in our first example. That's an identity that we've already proven, so we don't have to go the long route anymore. We can just say sine theta over cosine theta is tangent theta. We can apply that transitive property of equality. If A is equal to B and B is equal to C, then A must also be equal to C. So if sine theta secant theta is equal to sine over cosine, then it must also be equal to tangent, since tangent is sine over cosine. All right, that was example number 2. Let's move to our final example here, example number 3. We want to prove that secant theta to the 4th minus secant theta squared is the same as 1 over cotangent theta to the 4th plus 1 over cotangent theta squared. And remember, we want to pick the more difficult side to start with, and we want to simplify that more difficult side so that it matches. In this case, we're going to simplify the right-hand side so that it matches our left-hand side. All right, so you see that I've got 1 over cotangent to the 4th plus 1 over cotangent squared. The first thing I want to do is change each of those to the basic ratio, sine, cosine, tangent. In this case, 1 over cotangent is just the same thing as tangent, and 1 over cotangent squared is the same as tangent squared. So that's the first thing I'm going to do, is rewrite those as one of the 3 basic trig ratios. Okay, then when I look at those two things, I see that I can factor out a commonality. I see that I can factor out a tangent squared. So let me go ahead and factor out a tangent squared. And you may be asking, why would I factor out a tangent squared? It's because I see that my Pythagorean identity can be written in terms of tangent squared. This identity is 1 plus tangent squared equals secant squared theta. If I solve that for tangent squared, I can also say that tangent squared theta is equal to secant squared theta minus 1. So if I factor out this tangent squared, it looks like I can replace that with something else here. Remember, I'm trying to get from tangent to secant. And the identity that has both tangent and secant in it is the Pythagorean identity. So that's where I really want to head. So I'm going to factor out a tangent squared theta, which leaves me tangent squared theta on the outside and tangent squared theta plus 1. And if you look at my Pythagorean identity, I can then make some substitutions based on the Pythagorean identity. I know that tangent squared theta, I just wrote that one out. Tangent squared theta is the same thing as secant squared theta minus 1. There it is. And I know that tangent squared theta plus 1 is the same thing as secant squared. So I can replace my tangent squared theta plus 1 with secant squared theta. All right, remember that's where I'm trying to head. I'm trying to head to secants here. I was at cotangents, and I'm trying to move that to secants, trying to make that 6 degrees of separation here. All right, once I have those substituted using my Pythagorean identity, I can use the distributive property to simplify. So when I take secant squared theta times secant squared theta, I get secant theta to the 4th, and secant squared times -1 is negative secant squared. And now you can see what I simplified on my right-hand side matches on my left-hand side. So when you're doing these identities, you want to think about what trig ratio you're starting with and where you're heading. Think about what identities will help you get to that point. So I knew that by changing it to tangent and then trying to get it to secant, I know that my Pythagorean identity had both tangent and secant, so that would be a good one to help me out there. So this definitely is going to take some practice to recognize these identities and recognize what steps you need to take. It's not going to come quickly, probably, unless you are really solid in your geometric proofs, because the steps behind a proof, you really have to kind of think about what do I know and where am I going and what puzzle pieces or what identities do I need to get there. So it's a bit of a puzzle. For those of you that like puzzles, you may find this really challenging and enjoyable. I hope that it will become easier the more that you do that. All right, so today we stated reciprocal in Pythagorean identities involving trig ratios, and we proved trigonometric identities using these laws of proofs and algebraic identities and definitions of trig ratios. Now, I know that you probably have some questions, and we will definitely walk through a lot of these in class together, so no worries there. But if you have any other questions, be sure that you write those down and ask me next class.